we call the slope, the change in y over the change in x. So there's that. Okay. Going once, twice. Yes, sir. I didn't assign it, but we could. You want me to? Okay. 12 is the same as 13, except it's a little bit less work because you only have 3 lines instead of 4. So we've got Q is there, P is there, R is there. So PQ is this line here, QR is this line here, and then RP is this line here. And we've got the equations above it, y equals 1, 2x plus y equals 8, and 2y minus x equals 6. So again, we could do this using a table of values, or we could put these into that other form, slope-intercept form, and solve it that way. I don't particularly care which way you want to do it, so Jay, tell me which way you want me to do it. Let's do it. So y equals 1 is already done. In fact, y equals 1 is what kind of line? It is, Angel? It's horizontal, because y is always equal to 1. So where y is equal to 1 is right there, and x is allowed to be anything. So QR is actually going to be on the line y equals 1, so that guy's done. Now this one, I got 2x plus y equals 8. To get y by itself, and it's already positive, what are we going to do? I'm going to subtract 2x. So to keep us in the form that we're used to, I'm going to write it as, when I take away 2x, I'm going to write it as negative 2x plus 8. Of the lines we have left, only one of them has a negative slope. Negative slopes go down to the right instead of up to the right. Which one is going to land on negative 2x plus 8? PQ, QR, PR, or PQ? PR. So then this guy here is going to be 2x plus y equals 8, which means the last one has to be, without even doing any work, this one has to be PQ. But we could prove it. Let's isolate for y by adding x to both sides. So I'm going to get 2y equals x plus 6. I'm going to divide by 2. So I'm going to get y equals 1/2 x plus 3. Because when I've got a numerator, I can divide both parts of my numerator by my denominator. Because I've got separate terms here, this only works because I've got x plus 6. So this becomes 1 over 2x plus 3. So I want a line that has this y-intercept and this slope, which means I go 2 in the x and 1 in the y. So that right there is my intercept. So I'm going to go over 2 in the x, up 1 in the y, and so it's got to be this line here. So this one is 2y minus x equals 6. That's 12. We good? If we're struggling with any of this, please do ask. And I think I encouraged you at the beginning of the semester, but I'll say it again. If any of you, I'm all for tutors. Tutors are great. I was a tutor in high school and in university. It's a great way to make money for the tutor, not for you, because it's expensive for you to go to a tutor. I made a killing as a tutor. If you're spending a bunch of money on a tutor but not taking the time to get help from a math teacher in the building who is happy to help you for free, I would strongly encourage you to approach, and it doesn't even have to be me. If you're like, I didn't understand it in class, so why would I ask Deweydoff for help? He's a jerk. I can introduce you to 1, 2, 3, 4, 5 other math teachers in the building that might be able to explain it to you differently, perhaps better, cheaper than a tutor, and either meaner than me or friendlier than me, depending on your choice. I can introduce you to an angry version of a math teacher who is, I'm sure, happy to help. He'll explain things different than me. A happier version, she'll explain things different than me. An older version, you'll have him when you hit year 1 or year 2. It's math department head, Mr. DeVries. So, by all means, get a tutor if you're struggling and want a tutor. But do know that there are people who are willing to help you for free if you're willing to give up a little bit of your lunch or a little bit of your after school to get help. And again, it doesn't have to be me. If you are convinced that I cannot help you because you don't understand what's going on in my class, I am happy to introduce you to other math teachers. I will not be offended. A little sad, but not offended. But I am an adult who can deal with my own emotions. So, and as math teachers, I help DeVries' students. I help Keeley's students. Myers has helped my students. Like, it's just, we don't care. We're happy to assist each other and our students. So anyway, last lesson out of this chapter. Sorry? No? Sorry, Chelsea? Okay, you look like you had a question. What? I heard a voice from over there, and her eyes were like expectant. Carmen, was that you? There's a question? Okay, you know what? If there's not a question, we're going to move on. Last lesson, here we go. Unit 4, lesson 6. There are some words here that we're going to define. We love defining things in math. We've got two concepts here. One is called interpolation, and one is called extrapolation. Hands up if you've ever heard these terms before.
I've heard extrapolation, but I have no idea what it means.
Okay.
It's like what they do in, like, when they mummify somebody, they like take the...
Well, that's extract.
Well, no, but there's like a...
That's a helpful word.
What's the tool called where they take the...
A fork?
The nose. Scalpel. It kind of sounds like extract and scalpel and like...
Extract. Okay. So what do you do when you extract something?
You take it out.
You take it outside of where it was.
Yes.
So we're clearly not going to be doing this. But if we're extrapolating something, that it's the same root or the same suffix there, prefix. It's the same prefix there. The beginning of the word is the same. So what we're going to do is we're going to look outside of where we are when we extrapolate. We're going to look outside of where we are, which is going to make more sense here when we actually do it. And I'm going to put the R in quotes, because we're not where we are in three-dimensional space. You're in my classroom, and we're not going to go look outside my classroom. But we're going to look outside of where we are in terms of the graph that we've created or given. So if extraction or extrapolation is to pull things outside or to look outside of where we are, what do you think interpolation might be? Well, we are looking from inside already. Maybe it's what you meant and just the way you said it was. Yes, we are going to look within. We are currently in, and we're going to look further in. We are going to look within. Where we are. And I'll put R in quotes there. So interpolation is like inside, and extrapolation is like extracting something. To extract means to pull it out, to remove it, to throw it away outside of where we are. So let's do that. Let's interpolate first. So let's graph this thing. I've got data. The following table of values is data recorded during a running race. Time is in minutes, distance is in kilometers. For 5 minutes, 1 kilometer, 10 minutes, 2 kilometers, 20 minutes, 4 kilometers. Sorry, what? Am I stopping? Okay. 40 minutes, 8 kilometers. So let's graph this. We have no scale. We're just given a set of axes. The data that we're given, is it going to fit on this graph the way the graph is outlined? It's all positive, so we're good, but if we just have no labeling on the scaling, we assume the scaling to be 1, that's going to be, right, it's going to be problematic, isn't it? She's like, no, this is bad. This is terrible. So let's pick a scale. Danny suggested our scale to be what? Danny, say that again. every one of these lines to be 5. Okay, cool. Let's do that. 5, 10, 15,
So it'll actually be precise.
20. What are we putting on the bottom axis?
The distance, I don't know.
We are putting time.
Yeah.
Well, you said go up by 5, and so I started, but that must mean time.
And then,
Time is always independent as far as when we're analyzing something that's already happened. So, and and then, sorry, which axis? The D or the y-axis. So this is going to be distance going up here on the y-axis because distance depends on your time. Carolyn has suggested that we go up by 1s, and that works. It fits. 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. Let's put some points on here. 5 and 1 is going to go right there. 10 and 2 is going to go right there. 20 and 4 is going to go right there. 40 and 8 is going to go right there. Does it make sense to connect these dots? Why? I can have any fraction of time and I can have any fraction of distance. So let's connect the dots. I have a ruler. Use whatever straight edge you got handy. Side of a binder, whatever, I don't care. Your own ruler if you've got one. That doesn't, it looks beautiful on my page, but it's not dark enough on the board. So let's do some extra coloring in there. There, can we see that? We totally can, excellent. So interpolation is looking within the data that we've already been given. So the data we have spans from 5 minutes to 40 minutes. How long does it take the runner to travel 3 kilometers? How'd you do that, Rebecca? Oh, so you made the equation. That is not interpolation, but that is a smart way to do it. Interpolation is to look within our data and see if we can just read it off what we've got. Carolyn. So 3 kilometers here. What do we do with that? We go over to the line. The line is our relationship between these two things. And then go down. So what's our time? 15 minutes. Which, interestingly enough, is the exact same answer Rebecca got by recognizing that the change in y over the change in x is 5. So the equation for this graph is d equals 5t. So she just plugged in some variables and solved it. That's great. Unfortunately, not the skill I'm trying to teach you right now, because everybody tried. We're good there.
Because I saw that too. I was like, oh, they're all like times 5 and they equal the time.
Yep.
You know, but I didn't get with more complicated numbers where I wouldn't get the equation. But I guess that makes so much sense when you just go to the y-axis or the what do you call that? Did you call it the y-axis or the?
Yep.
Yeah.
Distance axis, y-axis.
No, then you go to the what's that? What we call the line?
The line.
Just the line.
The line.
Okay.
There was only one.
That makes a lot of sense. Just to go to the line and then down again.
Yeah. Because that is the purpose of the graph. The purpose of the graph is to give us a relation between. Oh, you took 2. Nice. Riley and Lalith both have leadership laptops. We'll give back. Sweet. I just noticed that they were missing off my desk there, so I assumed you took one. I didn't notice the second one. Yeah. Any issues with? Oh, no, you're not in that class. Never mind. These guys wanted to brag about how close they got in GeoGuessr to my Physics 11s. One and a half meters.
We did one in Mexico City, and we were 3 kilometers away.
That's pretty good. These guys got within 1.5 meters.
No, 1.
1 meter. Sorry. 1 meter. Wow. Okay, next question, B. How long does it take the runner to travel 6 kilometers? Well, we're going to use we could jam it through our equation, or we just read it off the graph. We go to 6 kilometers. The line is what gives us the relationship there. 30 minutes. We could do the opposite now. How far has the runner traveled after 35 minutes? Where are we going to start this time? down here, and we're going to do what?
So up into the line and then across. Okay.
How long? How far, rather? Done. No. 7 kilometers. That makes more sense. Okay, yes, Presley.
I have a question with the equation you wrote down. Wouldn't it be either d equals 1/5t, or it could be t equals 5?
Yes, it's 1/5 t. D equals 1/5 t. You are correct. Why did you wait so long to fix it?
I was just making sure.
No, you were right. You were right.
That's what I was thinking.
And see, I'm gonna see you. Yeah, you were waiting. Yeah, you were right. D equals 1/5 t, because we go up 1 and over 5. I wrote it upside down. Up 1 over 5. Yeah, you're right. See, I told you. If it's something that I made, there's a very reasonable chance that there was a mistake, and therefore the tutor shouldn't get it. It's totally possible. But the process makes sense. Okay? So the idea of interpolation and extrapolation, don't make the equation, just look at the graph that we've created and use the graph to assume some things. Yeah?
Well, what we did made sense. I was like, oh, everything makes sense, but I don't understand how that's related to, like, what is what on the, what's, I can't answer those words. Extrapolation.
So what we just did is we interpolated.
Okay.
We looked within the data set we were given and found things that were within our data.
Just discovered.
We just used the data to graph a relationship, and then we looked, okay, so because I've got these wider data points, here's the beginning, here's the end, what was going on in between is what we did. Interpolation will make more sense when we extrapolate. We don't often interpolate. Interpolation is not as awesome. Extrapolating is much more useful. Yes, Amina?
You said that time is independent, but isn't time dependent?
Not when you're analyzing what's already happened.
You changed the formula.
I fixed the formula, yes.
Okay.
Yeah. No, time is independent.
But it could also be the other way around.
Distance is dependent. When you're analyzing something that's already happened, time is the thing that we always change to determine how far we've gone. Yes, you could reverse these, but then you're analyzing something different.
Okay.
Sorry?
Oh. Got it.
Okay, unrelated. Here we go. Interpolation will make more sense after we've now extrapolated. So, extrapolation is to look outside of where we are. So let's graph this again. I've got 5, 10, 20, 25, 10, 20, 40, and 50. Let's graph these things. Time is still going to be on the x-axis. Distance is still going to be on the y-axis. Are we allowed to use the same scales? No. What should our time scale be?
So how come?
Time can be the same. Yeah, let's do the same for time. 5, 10, 15, 20, 25, 30, 35, 40. Now distance, though, what do we got to do with distance? Going to go by tens? Okay. 10, 20, 30, 40, 50. And we're just going to keep going, fill the graph. 60, 70, 80. Okay, there we go. Now let's graph the data that we've been given in blue. 5 and 10, again, is going to be there. 10 and 20 is going to be there. 20 and 40 is going to be here. 25 and 50 is going to be there. Am I allowed to connect these dots? What's happening here? A bike race in time in seconds and distances in meters. Yes, we are allowed to connect the dots. Because we are allowed to have fractions of time and distance. So there it is. interpolation is what we did before. We looked within the data set we were given. Now, if you look here, question this one, D. Oh, that's an oops. This should be ABC and this should be ABC again. But what's not? I screwed up my listing, but that's okay. I'll fix it later. How long does it take the cyclist to travel 60 meters? Well, our data tops out at 50. So now we have to go beyond our data set to presume what would happen if we kept keeping data.
It's just distance divided by 2 time.
But the process is the same, yeah.
So 30. Or 30.
So Danny's created an equation already?
30 seconds.
D equals, what's the change in y and what's the change in x?
D divided by 2.
No, what's the change in y and what's the change in x? It's 10 over 5. So D is going to equal 10 over 5 times t. So D equals 2t.
Why can't we just leave it from the graph?
We're going to.
Yeah, that's what I was saying. Wait, D. Okay.
So let's read it from the graph. Let's go to 60 meters on the graph, over to our line, and now down. The procedure is exactly the same. We're just looking somewhere different. We're looking outside of our data set instead of within our data set. It's going to be 30 what?
30 seconds.
You betcha. How about 35 seconds? How far has... 35 up to 70. Good. 70 what? What assumption have we made here with extrapolation that we didn't with interpolation?
That the pattern is the same. I don't know.
Yeah, that the biker kept going and doing what he did before.
Yeah.
The biker was consistent up to 25 seconds. We're assuming the biker is going to continue to be consistent for the next 10 or 15 seconds. Who knows? Maybe at 27 seconds, biker crashed. He's done.
Yeah.
If biker crashed at 27 seconds, what's my graph going to look like? Let's draw a hypothetical. I'm going to draw the hypothetical. You don't have to. If at 27 seconds, Buddy crashed. There's 27 seconds. What happens as time increases if Buddy crashed at 27 seconds? No, very steep slope means he's decreasing his distance, means he's going backwards. Well, look what's here. It's distance. If here I go down, that means I'm decreasing in distance. If Biker Boy has crashed, he's on the side of the road.
Time would keep going, but distance would stop.
Time would keep going, but distance would stop. Now all of a sudden I've got flat. Buddy Guy crashed. That's what that would look like. What did I do to deserve? Always.
They made a mistake and didn't want to throw it down the drain. And now you're like, nice coffee.
They made an oops.
I know.
I love it when they make oopses. These kinds of mistakes. I'm sure it tastes delightful.
But it's an oops, right? It's not a bad one. Just
Love it. I will always drink the mistake iced coffees. Okay, so the assumption that we're making, the pattern continues. Where is my coffee cup earlier? Where did it go? Did anyone see? No. It's a black coffee cup. Now I'm.
what color is it?
I left it somewhere.
It's not the one with the straw. What color
It's not the one with the straw. Where did I leave it? Is it in my bag? This is really gonna bother me. It's not in my bag. This is not good. Okay, so that's as far. I'm gonna go look for it after I assign you guys some homework. This is really gonna bother me. That's like my favorite coffee cup. Okay, so questions, comments, concerns about what we've done here. Okay, hearing nothing. Flip the page. Yes.
So, what did we do differently? Because I'm really not seeing what we did differently.
All we did was we were outside our data set instead of within the data.
I don't.
Here, we had 5, 10, 20, 40 minutes. 15 and 30 are in between these times. We were inside the data. Here, we had 5, 10, 20, 25 seconds. And the questions were about, well, what happens at 60 meters and 35 seconds? These two things were asking us about things that were outside of the data that we had collected. And so when you're outside the data you've collected, it's extrapolation.
Okay, I got it. Okay.
That's all it is. Okay, so what I'm going to get you to do, there's 25 minutes left. Here you go. This page here, and some questions. Here, there. And then we're done. And I'm going to go find my coffee cup.